Imagine if by just slightly adapting an existing technology, you could supply the world's electricity needs 11 times over.
No, it's really tiny, but the potential is huge. The results we have seen is it's exceeding our expectations.
Developers are taking wind turbines to deep water where previously they couldn't. And instead of building them onto the sea floor, they'll float on the surface.
You're able to go much deeper into the ocean and thus catch more of the wind that's available.
Floating platforms could open vast new areas of the ocean to wind power, generating billions of dollars in turbine contracts, but also valuable clean energy.
If you could do floating wind in an industrial manner, then you could really do something that might be an important factor in the fight against climate change.
The race is on to develop cost-efficient floating farms that can become an almost boundless source of emission-free electricity. And there are already dozens of players competing to make the best design.
I feel a big pressure for us to succeed, not for the sake of our company, but for the sake of making the green transition happen.
Most of the world's energy today still comes from fossil fuels. That's coal, oil, and gas. None of those fossil fuels are on their way out as quickly as we need them to be able to meet global climate goals. Since the 70s, wind power has been on a slight rise, but it's really taken off in the last decade or 2 decades. One of the things that has made wind power more cost-effective in recent decades has been the increasing size of the wind turbine. They went from something you could look at without having to even turn your head up to almost the size of the Empire State Building now. The reason big turbines matter is because of something called the power equation, which is the square of the radius of the turbine, which covers its area, and the wind speed cubed. For every increase in the radius, there's a factor more wind power that can be caught from the wind speed. As wind turbines get bigger, they go higher into the sky. And the higher they go, the faster the wind that they can catch. And all of that helps make wind turbines that are bigger much more effective at being able to produce power.
Putting more turbines out at sea, where the wind blows stronger and more consistently, could mean generating even more energy, more cost-effectively. That means seriously modifying the designs of current turbines.
So when I set out to see if I could make a difference, I looked at existing designs and I looked at, so to speak, the mechanisms that were driving them. Oh, now there will be the clocks will chime. That's a classical English grandfather clock. Very, very nice. That one will do it and that one will do it.
Henrik Stiesdal is very fond of clocks.
And the one over there is a French middle-piece clock that one is from the 1700s, that's from the 1800s. The one in there is from the 1700s.
He likes their qualities: accuracy, simplicity, longevity.
And of course there's something sexy about a machine that has been running for 250 years. That's well done.
The Danish inventor is also very aware of time and that one day it'll run out. He's become a renewable energy pioneer, working with wind power since he was a boy.
My father said, let's go up and see a place where they're building a big wind turbine. So we went up and took a look at that. And I saw young people like myself. At that time I was 19. And I thought, well, if they can do it, I can do it also. And after some experiments, we found an aerodynamic shape that worked tremendously. So you would go out with this kind of dead thing and set it in motion. And then when it started spinning, it felt as if it got alive, because it could feel all the small eddies in the wind in a completely different way from when it was standing still. And then I was hooked. After that, I built a larger test turbine, and then I ended up building a turbine that would power my parents' farm.
Known as the godfather of wind, Stiesdal is linked with most of the industry's big firsts, patenting the 3-blade turbine that's ubiquitous today and launching the very first offshore wind farm in the world off the coast of Denmark. After working for some of the sector's biggest players, he retired, briefly. He's been tempted back to find solutions for a power-hungry world.
And there I landed on the idea that the combination of floating offshore wind, which is the only way you can do offshore wind in California, and to a large extent the most important you can do in Japan. So you don't always have the space available for onshore wind, you might not have the space available for solar. But with offshore wind, you generally have enough space. But there the challenge is that it only works up to about 60 meters of depth or something of that nature.
Building foundations in the seabed deeper than this makes turbines too expensive, and so offshore turbines are only built in relatively shallow water.
So one of the reasons why the offshore wind industry has done so well in Europe is because the continent is blessed with a continental shelf that extends into shallow waters for hundreds of kilometers from the coastline. That's not the case for most parts of the world. California, for example, has very deep waters very close to its coastline, which means they cannot use offshore wind turbines as a solution for their electricity needs. And that's where floating wind turbines can make a real difference, because they provide an option that hasn't yet existed in an economical fashion for tapping wind power.
Offshore wind can supply the whole electricity demand of the world as it is now. But it is fairly unevenly distributed, with many places not being able to exploit offshore wind because they just don't have the ocean conditions for it. If you instead introduce floating, or in parallel introduce floating, you can multiply the available resource by a factor of 10.
Making a wind turbine the size of the Empire State Building float out in the ocean is easier said than done.
Wind turbines are not cheap. They use expensive metals, there are magnets, there are those blades which have been hundreds of meters long, which have been constructed specifically for that purpose. So when you put a floating wind turbine out into the sea, you want to be very sure it will not fall over. The simple idea behind a floating wind turbine is that you need enough buoyancy to keep the wind turbine erect and above water. And you can achieve that with a simple idea like the boat's hull, where you put a certain amount of weight underwater that provides the buoyancy to keep it erect and catch the wind.
This is exactly what dozens of floating wind designs try to do. Many use the principles of a floating buoy to build a spar, a tube-like marine structure that relies on gravity for stability. It's then tethered to the sea floor. One of Stiesdal's designs, Tetraspar, uses several modular steel tubes.
So it's got three radials, we call them three laterals, and three diagonals. And what the diagonals do is that they help transfer the big bending moments on the tower in a smart way out to the structure. So that's why we call it Tetraspar. It's a tetrahedron as a geometrical shape, and it's a spar because it works with this center of gravity below the center of buoyancy. It stretches some 165 meters into the air. It's got a rotor that's 130 meters in diameter. The floater itself weighs more than 1,000 tons and is 60 meters from one side to the other. It can move about 30 or 40 meters away from its neutral position. When it has the full load on the rotor, it will heel over about 5 degrees. The turbine is a 3.6 megawatt turbine. That is a small turbine nowadays because the industry is developing so fast. If things work out as they should, it will generate about 14 million kilowatt hours a year. Well, in my home, we used about 4,000 kilowatt hours a year. So this turbine will power about 3,500 homes like my home. So even though it is by modern standards a small turbine, it still is something that you can say, that's kind of interesting. A town with 3,500 households is not a small village, and one turbine can power that.
Building smart green technologies will help save our planet. But to make a real impact, we need to burn fewer fossil fuels. Offshore wind is an important bridge.
One industry that has benefited from the offshore wind industry has actually been the oil and gas industry, because they have a lot of technology but also skills and experience working with offshore platforms drawing out oil and gas. Some of those skills can be applied to offshore wind power and to floating wind power, which means there is actually a route available, at least for some people, to be able to transition from what is a carbon-heavy job to a low-carbon job in the future, something that the world is going to need if it's going to transition away from fossil fuels.
Norway's Equinor is undergoing that massive transition. Formerly Statoil, the company produces more than 2 million barrels of oil a day and is the second largest supplier of natural gas in the European market. But it's made big strides into renewables, and it's also arguably leading the pack when it comes to floating wind. Their design is called Hywind. It's based on the simple spar principle, something the oil and gas industry has already been using to float platforms.
This location is excellent for building a Hywind spar, and the reason why it's sheltered areas is deep water areas close to shore. Equinor has been a pioneer within floating wind since the early 2000s, when we developed and installed the Hywind demo back in 2009.
Equinor's design is in use in a fully operational 5-turbine farm off the coast of Scotland. It's proving the technology's worth through higher than average capacity factors. That's the share of time the turbine produces electricity at peak capacity. The higher the number, the more value for money.
The Hywind Scotland has been the best ever producing turbine with a capacity factor of 57% at maximum for several years. The newest developed bottom-fixed projects and farms has higher capacity factors, maybe in the high 40%. But for sure, Hywind Scotland has proved that putting floating wind turbines in areas where you have a good wind condition is very favorable for floating offshore wind. And from Hywind Demo to Hywind Scotland, we see a cost decrease from capex per megawatt of 60%. From Hywind Scotland to Hywind Tampen, we're aiming for a cost reduction between 40 and 50%.
In Norway, another 11 floating devices are being constructed. Once complete, they'll be towed out to deep water. The energy the turbines produce will help power the company's oil and gas platforms, some of the region's biggest. Equinor says it will reduce CO2 emissions by 200,000 tonnes a year.
We will build our legacy from oil and gas and projects execution, marine operations, and that's why we went into bottom-fixed offshore wind and now floating offshore wind, is that we can use our competence, our experience, and for sure we can also finance these new developments within renewables because the cash flow we have from oil and gas.
That's another advantage the oil and gas giants have. This 11-turbine project is set to cost Equinor an estimated $600 million.
Within this decade, we shall invest as much in renewables as we do in oil and gas. It's not the proving of the concept, we have proved it, so this is kind of just the next stepping stone, and then we go for this industrialized wind farm. The cost battle will be the most challenging one to make this industry profitable, and then we need big volumes. There is a lot of things which need to happen at the same time.
Equinor has ramped up production in Norway by building its own on-site cement factory. It's an attitude of industrialization that could quickly determine floating wind's key players.
Among the dozens of floating wind turbine designs that are out there, one of the ways in which the winner might be chosen is based on how much material is used in the development of those designs. So the lower the amount of material used, the lower the cost of that floating wind turbine is likely to be.
So wind power has gone from being a costly alternative to being something that is nowadays competitive with fossil power sources. You say why? The main driving factor was industrialization. So mass production is the way to low cost. I have a mobile phone somewhere, I don't have it here, but I have it somewhere. I paid maybe $600 for it. And as you know, everybody knows, it's got like 100 times or 1,000 times the computing power that NASA had when they sent people to the moon. If I was to build that one from scratch, it would not cost $600, it would cost 6 million or whatever. The reason I can get something with all that power is because it's mass produced. And that's also what has come into wind power. Prices kept dropping, because we produce things in big numbers. We have designed a structure that is modules that are built in the factory in the right length, so that when you have this piece of steel plate, you can roll it into what we call a can, and then you simply weld it where it got rolled together, and then you put it together with neighbors and weld them all together with a round C. And getting that to work is what Welcon is super good at. And then they are transported to the port, and in the port they are assembled, and then the floater is launched, you put on the turbine and tow it out to the site.
As with any technology in its nascency, it feels a little fanciful to imagine what a world full of that new technology would look like. But we've seen that happen time and again, with solar panels, batteries, and electric cars. So there's no reason to think that can't happen with floating wind turbines.
Beyond 2030, I strongly believe that we will see big-scale wind farms, which is profitable, and we will see also that the ramping up, that this will be a big industry going towards 2040 and 2050.
If you were to do theoretical calculations, pretty much any type of renewable energy will be able to provide all the power that the world needs. Be that building solar panels in the middle of Sahara and then cabling the world with them, or building, say, floating wind turbines in the middle of the Pacific and doing the same. So there isn't a limit on how much power renewable energy can provide. What is a limit is how much money we can spend to be able to access that power.
The competition in floating wind could be brutal. Inevitably, some companies will lose out and maybe go bust. For now, the competition can only be a good thing.
We cannot create all the volumes. We need also volumes from our competitors. So we think that this competition is important for industrializing floating offshore wind.
And it could be that there could be several of them who simply outsmart us and do it in a better way. And that would be okay, because what we are doing this for is for the climate. So if somebody comes in and outcompetes us or outsmarts us and says, yeah, I heard what you said, I kind of agree on the industrialization way, I just found a smarter way to do it, he or she would be my friend.